So in interfacing, how to interface external world to the microprocessor through 8255 is what we discussed. And now we are going to deal with any sensor. In the last class we have seen any sensor, how it can be interfaced to 8086 through analog to digital converter. So is what we have seen. So now let us try to interface A to D converter to 8086 microprocessors. Right. So comfortable programming point we didn't see. So now let us go ahead with interfacing of analog to digital converters. So let us see the hardware of analog to digital converter. So now we have seen, like, this is what your microprocessor 8086, and now here is your sensor. The sensor could be anything, right? Temperature sensor or pressure sensor, anything. So you want to process the real-time information using microprocessors. So the sensor data is analog. So the output of sensor is an analog form. So now what we need to do is we need a to D converter. So we need a to D converter. So this A to D converter converts the analog signal into digital. So now let us take, you have an 8-bit A to D converter is. So now this A to D converter, the digital output from the analog to digital converter has to be read by the data bus of microprocessors. So when you are interfacing or when you are connecting external devices to the microprocessor, directly you cannot do. So you need 8255. Through 8255 is what you need to do. So here you have the data bus of 8255 is connected to data bus of microprocessor, right? And now here we have ports, right? We have ports. We have port A, port B, and port C. So if it is 8-bit analog to digital converter, let us take an example: 1, 2, 3, 4, 5, 6, 7, and then 8. So if the output of A to D converter, if it is 8-bit, so you can connect this to any port. So port A is of 8-bit, port B is of 8-bit, and port C of 8-bit. So you can connect any one of this to 8255. So up to this particular point is what we have seen in the last class. So here you have a sensor, right? Here you have a sensor. So the sensor output you need to analyze by using your processor. So then you need to interface this through 8255. So up to this particular point we have seen. So what hardware we need to interface your real-time signals to the microprocessor, sensor signal using microprocessor is what we will see. So now let us go ahead with this background in mind. So now let us try to see this particular point. Let us take an example. So yeah, so this is what the example we are trying to take, and the analog to digital converter IC is 0809 is what we are considering. So it is, see, if you want to interface sensors to the 8086 processor, you have to know the hardware. So A to D converter IC, if you try to see, it is a 28-pin IC. So here you can see very important signals, like what signals of what signals of this thing, no, if you try to see here, there is a start signal here, there is a start signal. That means you have to, here, if you have an analog to digital converter, you have to give a start signal for conversion. So you have to tell it like, you start, analog signal is available, then you can start. So you can connect your analog signal to any one of these points, IN1, IN2, IN0. So IN0, IN1, IN2, input 3, 4, 5, 6 and 7. So that means the ADC0809 is A to D converter. This A to D converter, you can give 8 analog signals. Then you have to be particular, you have to be particular about where your sensor is connected. Right. So your sensor, maybe that means at a time you can connect 8 sensors to analog to digital converter IC, and you have to pretty sure like where you connected your particular sensor. Now your sensor can be connected to any one of these 8. So the selection of this any one of these 8 can be done by using select lines. So this is A, B and C. Let us take if A is 0, B is 0 and C is 0. The sensor, the analog to digital converter selects IN0. That means the sensor is connected to IN0. And if it is 001, right, now let us take if it is 100, then the sensor is connected to 1, then 2, 3 like that, based on the select lines. Okay, so you can select where your sensor is connected. So here you have an important signal, start signal, and here you have an important signal, end of conversion signal. That means how do you know, like, you connected your sensors to any one of these analog inputs and you gave a start command. So when you gave a start command, how much time the analog to digital converter takes to convert your analog signal into digital signal. So that can be known by using a signal called end of conversion signal. So the moment the analog to digital converter starts conversion, then this end of conversion signal will be going low, and once the conversion is finished, then it is going high. So you have to keep on checking this end of conversion signal whether it is low or high. Okay, whether it is low or high. So that is about the task of end of conversioners. Right? Then so this is about start of conversion, end of conversion, and selection of any one of the analog inputs, and the digital outputs. No, the digital outputs are available on the LSB. Now you see here the LSB is 2 power and 8-bit converter. If you can take this, right? So then here you have this is one LSB, I mean this is one digital output, this is one digital output, 1, 2, so 1, 2, 3, 4, 4 and then 5, right, 5 and then 6, then 7, right, then 7. So it is 8-bit converter, so 8 digital pins. So here if you try to see the input of the analog to digital converter, so here the input to the analog to digital converter is 1. That means one sensor I am connecting, but the output here is an 8-bit. So the 8-bit is of this 8 pins. So you need 8 pins has to be connected to any one of the port, and then you have to give a startup conversion signal. So that means the processor, it has to give a startup conversion signal. So it has a startup conversion signal, and that has to be connected to somewhere else. And then it is having end of conversion signal for checking out your conversion is done or not. And then you have to select, your sensor can be connected to any one of the analog inputs. So then here you have 3 signals like, channel, select channels, like selecting any one of the analog inputs can be done by using this. So we need to deal with 3 plus 1 4 plus 8 12, 12 plus 2 16 pins, 16 signals. We should know about interfacing, need to be interfaced to the 8255. So now let us see how it can be done. So the conversion can be done by using a reference voltage. So here you have a reference voltage, right? And yeah, that is about the hardware. And how fast the conversion does, that depends upon the clock signal. So the clock signal which you give, and output enable. That means once the conversion is done by using ADC, then the signals, that means the data is available. Now if you see the internal diagram of this which we are talking about, so the internal diagram, if you try to see here, you have 8 analog inputs, and 8 analog inputs can be selected by using address lines, right? Address lines. So, or we can say there is a multiplexer. So these are the select lines. So based on the select lines, you can select any one of the analog sensor. But here this we may select, like I can give a command 011 on this 3-bit converter for selecting the third analog input where my sensor is connected. But this data has to be, that means the microprocessor we are connecting here. So the microprocessor has to tell like from where you have to get the digital data. So at that time we need, that means to send this data into the latch and decoder, you need to give a pulse signal here. So pulse signal here at address latch enable, so that whatever you are writing here, it goes into the latch. Analog signal is selected. So these are the steps, the things which we are discussing. It should come in the form of an algorithm, and that algorithm should be converted into the instructions. Right. So with the steps, the procedure, you have to know very clearly. So the first step is what? You have to know where your analog sensor is connected. So once you know the analog sensor, then you have to select that analog sensor by using select lines. So you can give a command like, if it is connected to the first sensor, then you can give a signal 001, right? Or 000 could be first sensor, 001 could be the second sensor. So, but this data, when you try to give, this has to be sent into this particular A to D converter IC by the microprocessor. So this sending process can be done by using a latch enable. It means here you can give a pulse here, so that this command will goes to the latch and then the decoder. So then the decoder picks up any one of the analog channel. Then that analog channel is connected here, and then here you have a successive approximation type analog to digital converter, which is quite fast, okay, very fast we can say. And then the output is available in the tri-state buffer. So once the digital, so that you can check by using end of conversion, and you can give start of conversion signal. So you can give start of conversion signal, right? And then you can check for end of conversion signal. Once the end of conversion signal is going high, then the data is available on the data bus. So this is what the sequence is. And once the data is available in this IC, to bring the data onto the data bus of the microprocessor, then we need to give a pulse on this output latch enable. So that means here we have one more signal which we are seeing here, which is output enable. This output enable is what the signal we have to give, so that output enable, it brings the data which is there in the buffer onto the data buses. So this is the sequence need to be followed. Right. So about this particular IC, this 8-bit IC, and then the conversion time is 100 microsecond, very fast. Single supply 5 volts is enough. 8-channel multiplexed with latched control logic, easy to interface to all microprocessor, and low power consumption of 15 milliwatts. Right. And the minimum SOC pulse width. So these are the clock frequency you can connect to 10 to 1280 kilohertz. So the conversion time could be 100 milliseconds to, right, 100 milliseconds at 640 kilohertz. Generally we'll be connecting around 98 kilohertz in the lab. 640 kilohertz is a little high, but the conversion time is 10 milliseconds. 10 milliseconds is all right. Resolution 8-bit, right, it is an 8-bit digital bit which is there at R8. So this is what the this is what the hardware details of the ADC 0809. And now if A is 0, B is 0, C is 0, channel 0 is selected, and then if it is 001, channel 1, and then 2, 3, 4, 5, and 6. 6 and 7. So 8 channels can be selected like this. So now if you try to put the things which we discussed up to now, so you can write an algorithm. So the algorithm is, so this is what the algorithm or steps you need to follow. You can say, so select the analog channel by providing bits to ABC. That means you have to know where your analog sensor is connected. Then now you have to activate the ALE pin. So now you try to see the ALE pin here. So ALE pin, where it is, address/enable. So here if you try to see the hardware details, that is output enable, start, and then yeah, the 22nd pin. The 22nd pin is ALE. So this ALE is to latch the command which you have written to select a particular channel. So that is what it is written here. So the second step is activate ALE pin. Activate ALE pin means what? You have to generate a square, a pulse on the ALE, so that what you are writing on this ABC of the channels, it goes to the A to D converter, and then that particular analog input is connected to the A to D pins. Then now you just start or activate your startup. You activate the conversion process by you giving SOC a low to high pulse. So here you have to give a low to high pulse to initiate conversion. Right, to initiate conversion, you have to give a low to high pulse on SOC. And now you need to monitor the end of conversion signal. And if end of conversion signal is going low, then the data is available in the buffer. And now you give a pulse signal, right? You give a pulse signal now, and then if you give a pulse signal, whatever the data is available in tri-state buffers, it comes onto the data bus of the 8086, and you can move it into your any accumulator register basis. So this is the algorithm you need to follow to read the data of 8086 microprocessor. Now go through this. This is 0804, 0804 or 0809. This is almost similar. Check it out. So here you have your 8086 microprocessor you can consider, and this is data bus. So this is your digital output, and just give a glance. So here I have a potentiometer. So the potentiometer is connected to 5 volts. Right. So potentiometer will have 3 pins. Right, 1, 2, and 3. So this is connected to 5 volts. So it is a variable resistor. So this resistor, if it is moving, if wiper is moving on this, the resistance will change. When the resistance is changing, the voltage is changing. So that voltage we are reading by using 6 and 7 pins as a differential input of this particular ICs. Right? Then we have to select the chip select of this particular analog to digital converter IC, and read bar and write bar, so they are there. Now just check it out. Here you have this particular IC is what we are dealing. So now hardware, it is pretty sure, like you have to know the hardware. Unless you know the hardware, you cannot do any programming. So now you assume, like now you can assume the sensor is available, the sensor is connected to input 1 of A to D converter. So now let us formulate a problem. So now you can consider there is a potentiometer. So the potentiometer has 3 terminals. So this is connected to VCC, and right. So these 2 signals you are giving it to A to D converter. A to D converter. Right. So now you see, take down the problem. Yeah, so then here any one analog input. So analog input means now you see the thing. So where the analog input you can connect, right? V reference and V reference. So here you are going to connect. So this is what you are powering up VCC, right? And then so this V reference and V reference, so 12th pin and 16th pin. So 12th and 16th pin is what you are connecting, right? So you can assume, like your 0809 is what we are trying to see. So 12th pin and 16th pin is what you are connecting to A to D converter, right? No, that is what the reference. I'm sorry. And here you can see like IN0, yeah, IN1, the 27th pin, it is what it is connected is. 27th pin is what it is connected is. So you can take this is 27th pin, which is of IN0. Right, so which is of IN0 is what you can consider of analog to digital converter. Right, so this is what the reference, so this is what the VCC. So now you have to give start of conversion here, and now you have to give end of conversion here. You have to read the end of conversion here, and 8 digital bits are output. So these 8 digital outputs are connected to 8255. So 8255. Now let us take this example. Anything is all right. Okay, any example you can consider. So now if this example you consider, so then startup conversion is right. Startup conversion. So you can assume, like this is giving startup conversion. There is no read bar kind of thing here. The analog to digital converter IC. So you can give like startup conversion, and then you can read end of conversion signal here. So you can modify this, is a little bit example you can take, right? So end of conversion signal. So here now if you try to see this, all steps need to be followed. Then the flow chart which need now you see, let us formulate this. So if anything is given to you, like yeah, if anything is given to you, like this, A to D converter. This A to D converter can be connected to port A, right? Port A, right? PA0 to PA7, right? And then you can select your channel, your analog input by giving to 3 pins. So you can choose port B0, port B1, and port B2. So these select lines you can connect it to port A of your 8255. So this is your 8255, right? And so this is port A0, port A0 to port A7, right? And now startup conversion can be connected to any one of the port pins. So you can use port C or anything you can use. It's not a big deal. So port C is what? Port C0 is what I'm connecting port C1, and port C0 is what I am connecting to analog to digital converter. So you can assume this as start of conversion, you can assume this as end of conversion. So I need around how many pins of 8255? So 8 here, 3 here, 11, 11 plus 2, 13 pins is what I need. Okay, 13 pins to interface this to 8255, and then here it will be your 8086 microprocessors, right? So now let us start writing the program to read the voltage here. The moment you vary the potentiometer, the voltage will change. When the voltage is changing, the digital bits will change. So that you read in 8086, and then you can go back. So like that, you have to know the hardware first, right? You have to know hardware very clearly, and once you know the hardware, then you can go ahead with the program point. So now take this flow chart. So you first select channel, send start of conversion signal, then you wait for end of conversion signal. If end of conversion signal is high, right? If end of conversion signal is high, that means what? Right, that means the conversion is done. If not, you wait here only, right? And then read the digital data. So this is what the simple flow chart, right? So the same thing, it is drawn in the form of waveforms. So first you are giving your signals on PB0, PB1 and PB2, the example which we are considering, and you can select this, okay, is it all right? Yeah. So take case of analog to digital converter, right? And then we have seen the algorithm. So then we consider, right? We considered this kind of thing, like this kind of situation where 0809. So this is what your 0809. Yeah, 0809. So this is what your 0809 IC 0809 analog to digital converter IC. So this is your analog channels. So analog channels. Then this is what your digital bits. Right. This is what your start of conversion, and this is what your end of conversion signals. Right. So interfacing, hardware details and all we know now. So now we have to write an algorithm and then program. Right. So now if you try to see the steps which you need to follow here is this. Now, algorithm. Step number 1. So step number 1, what you need to do? Here you have to select where your analog pin is connected. So we have taken an example here. So sensor 1 means your sensor. Now you are assuming this as a sensor where you are getting a DC voltage. So it is connected to IN1. Right. So that has to be given input to your analog to digital converter. So that you can do. Right, by now it is PB0, PB1, PB2, PB0, PB1 and PB2. So PB0 and PB01, PB2, if it is given 0, 0, 0, IN0 will be selected. But what we need to select? IN1. So 0, 0, 1. So this is the command. We need to give it to port D. So we have to give it to port D so that here 0, 0, 1 will be appearing on A to D converter and then IN1 is getting selected. Right. So now let us start writing algorithm. So now configure 8255. So 8255, how you need to configure here? Port B as an output, right? Because you are giving here bits, so this is output, and port A. So once the conversion is done, the data is available on port A0 and this thing. So port A as input, right? And port C 0, you are giving a startup conversion signal, and port C1 you are reading the end of conversion signal is, right? So now let us put the same thing here. So configuring 8255. So 8255 means here you have to give port B as output port and port A as input port, right? So port B as output port, port A as input port, and port C, here we have to use input and output both. So that means, we have to read end of conversion signal, right? And then there you have to write. So you can make port C upper and port C lower, any kind of thing, right? So here what you can do is, in the hardware, this PC0, right? This PC0 is what you can connect it to startup conversion signal, and then this you can say like PC3. So PC0 you can make an output and PC3 as an input. Not PC3, this is PC0 means PC4. While port C lower, port C upper. So you can divide that 8255 into group A and group B, right? So group A and group B means, group A is port C upper and port A, and group B is port C lower and then port B. All right. So that way you can consider. So here, so port C upper you can make as input port, and port C lower you can make it as output port. This is how you have to configure your 8255. So this is why it is considered analog to digital converter interfacing to 8086 a little bit complex, but if you can follow this, the same thing you can extend it to the microcontroller when you need to read data from outside world into the microcontroller is. So this is what the first step. Now the second step. So configure, you can configure by sending a command word, right, as this way, right? And you can use BSR mode also, because you have to give a startup conversion signal or kind of thing. So anything you can follow, right? There is no standard way you can interface, right? So this is what step number one. Then step number two, send 001 on port B for what? To select input 1. Input 1, you have IN0 to IN8, so 1 is what where my the potentiometer is connected, right? So now step number 3, right? So you give on this, then next, then what you have to give a pulse on ALE. So here we need, like, to select this, we have to connect one more. So signal here, that is ALE of analog to digital converter address latch enabled, so that whatever we gave on port B0 and all, it goes to analog to digital converter, so that that equivalent analog thing is decoded. This ALE has to be connected, so this can be connected to PB3, right? PB3, or you can use any one of the thing. So there is also one more hardware details. So pulse on ALE, give a pulse on ALE. Right, so this giving a pulse on ALE, it can be done by using very easy process, right? Putting 8255 in BSR mode, bit set reset mode, and then in bit set reset mode, any port C pin you can make it high, low, very simply. So pin programmable means bit programmable way you can go ahead, or otherwise you can use the port B3 and then there you generate a square, right? So is that all right? Okay, so then take care, like, instead of connecting it to PB3, so you can connect it to PB4 also. PB4 also you can connect, not to disturb with this selection. Right, PB0, PB1, PB2, and then this you can connect it to PB4 too. Right, so then the next step is what? Give a pulse on ALE. So this ALE is connected here in this example which you are considering to PB4. Right. So then step number 4. So in step number 4, that particular thing is IN1 is connected to the input of the 0807. Then give start of conversion signal. So start of conversion signal, where it is connected. So start of conversion signal is connected to PC0, right? So you can give a pulse, or you can give low to high pulse, right? So you have to give a low to high pulse on PC0, so that it is equivalent of giving start signal. Then the next one is, then read EOC signal, or check EOC signal. So this is connected to PC4, so you read PC4. So PC4, if it is low, then PC4, if it is low, then conversion is still in the process. If it is high, then conversion is done, right? So then step number 6. So if then wait there only. If it is high, then conversion is over. Right. So check it is. So you have to write a condition here. So PC4 is what you can consider and you can go ahead. Then what do you need to do? End of conversion also like it high. Then there is one more signal, that is output enable of A to D converter. So output enable, so A to D converter output enable is what you can connect to PB5. So there is one more signal of A to D converter, which is output enable. So this output enable you can connect it to PB4. So see, this is what example where we are using all port pins of 8255. Right, all port pins of 8255. Right, so 2 here and 3 plus 2, 5 here. So 5 plus 2, 7, 7 plus 8, 15, right, 15 pins is what we are trying to interface here by using 8255s. So now step number 6 is what? Give a pulse signal on PB4. So PB4 is what? Where it is connected to output enable. So it is connected to output enable, which is nothing but, sorry, PB5 it is. PB4 anyhow we are using for some other purpose. So you have to give a pulse here. Right, so you have to give a pulse here. That means give 0 0 for some time and then give FF for some time. That's it. And then give 0 0 possible to give a pulse. Right? Then now once this is done, the data is available. So the hardware is such in a way we are connected. So it is PA0 is internally connected to data bus of 8255. The data bus of 55 is connected to 8086. So now you can read this data into your 8086 microprocessors. So now you can start writing your code. Right. So now you can take the addresses of port A, port B and port C and differently, like based on the kit which you are using or how you are interfacing as general. Okay. And then you can go ahead. So now the thing is here, port B as an output. So the control word is what you have to see. So it is D7, D6, D5, D4, D3, D2, D1 and D0. So this is what the control word of 8255. So we are using 8255 in simple output input mode, not DSR mode here. So this should be 1. And we are using mode 0, input or output. So this is group A. So group A means port A and all. So this is 0 0 is of mode 0. And D4 is port A. Port A we are using it as input port. Right. And D3 is port C upper. Yeah, port C upper. So port C upper, we are using port C upper means PC4 is what we are using, which you are using as input. So then make it as input. Then D2 is of group B control, so mode 0. If it is 0, then it is mode 0. Right. And D1 is a port B. So port B, we are using it as an output port only, so make it 0. and port C lower. So port C lower, we are using it as output port, so make it 0. So it is 9 and it is 8. So the first thing is, the instruction is move AL comma 98, move DX comma, the control DX is what the control register address. So which can be FFF, F0 or whatever it is. Right, control register address of 8255. Control register address. And out DX comma AL. So this configuration which you are thinking about, port B as an output, and port B also we are using port B as an output, but port B lower and upper is what we are trying to see here again, and port B, B4 and B5 is what we are using as an output. So port B as an output we are using, port A as an input. So this first step is done, right? And now you have to send 0001, right? 0001 signal. So step number 2, so 001, so it is 01 can be sent to port B. So move AL comma 01, move DX comma port B address, out DX comma AL. This is step number 2. And it is step number 1. Right? And step number 3 is give a pulse on ALE. Yeah. Right. So you have to give a pulse. So you have to give a pulse means here pulse is this. So this you have to give it on PB. This you can give it on PB4. That means giving 0 0 for some time and then 1 1 sometime. So move AL comma 0, already it is 1, right? So higher byte you can take it as 0, no problem. So 0 1 and move DX comma port B, out DX comma AL, and move CX comma some delay, this delay, right? Some delay. The same address you can give here. Then move AL comma F1. Anyhow, 1 is channel 1 now. So F means PB4, we have to give 1, right? PB4, PB5, PB6, PB7. 1 1 1 is what equivalent of F. Already we gave here, then PB0, so it can give F1. So then move DX comma port B, and then out dx comma al, and so this is what you are giving 0 for some time, and then high, low to high you are giving. So then here you can say like move cx comma 1 2 3 4, and then loop here. So this is how you can generate a low to high pulse. And again you want 0, then what you can do, move al comma 0. So you can repeat this. Move al comma 0 1, right? Because so that this PB4 and all will become 0, right? So here you can write move al comma 0 1, al comma 0 1, move dx comma port B address, and out dx comma al. So I gave a delay, and then I gave 0. So this is step number 3. Right? Okay, this is step number. Then step number 4. Step number 4 is give start of conversion signal PC0 a low to high. So you can follow the same thing what we discussed now. That means here in program what you can do, you can write move dx comma port C address, port C, right, port C address, a 16-bit address you can take, and then move PC0, we have to give low to high. So move al comma 0 0, and out dx comma al, and move al comma 0 1, and out dx comma al, and here you can give a loop, move cx comma 1 2 3 4 h, out loop here until the counter becomes 0. Until the counter becomes 0, it waits here. So we are trying to give here, this is step number 4. So it is step number 4, giving a low to high pulse on PC0. PC0 is connected here. Then what is step number 5? Step number 5 is read EOC signal. Right. Read EOC signal. So then move dx comma port C address in al comma dx. So port C upper is anyhow configured as input port. So then input port means here it is connected to PC4. So if PC4, if it is 0, conversion is still going on, otherwise you have to wait. So then what you can do, you can check this particular thing, and al comma 0 0. So if and al comma 0 0 means if PC4, if it is 1, then conversion is over. Right. So if conversion is done, then you are doing logical AND with 0 0 0. So result will be 0 0 0. So jump on 0. Right. Jump no 0. JNZ. So back. So you can go. You can be here. You can read right, and AL comma 0 0, right, and then you can do this declare operation as, right. If the data here which you are getting is 0 0 0 1, right, logical and you are going, so logical and AL comma 0 1 jump on 0, right, so logical and you are doing, so if it is 0, the input if it you are getting 0, I am doing with logical and 0, so if it is AL end of conversion is 0, then I'll be getting 0, if it is 0 means conversion is not over, be here. So this is step number 5, reading and checking out the end of conversion signal. Right. So this is step number 6. See, we are taking an example and then we have written the algorithm and then we are trying to write on a program. Right. So you are checking this with 1. So if you are the reading the data, if you are getting 0 0 0 1, you are doing AND with this. So when then both are 1, then a logical AND output is 1. Then at that case it is not 0, then it will come out. So if it is 0 means what? Conversion is still in the process. So this is step number 5. Then give a high pulse on, give a high command on your output enable. Right, so that you can do, right, and then you read port A. So this signal you can 6 and 7 you can go ahead, and 7 outer output enable, then you read port A. So once the conversion is done, that is available on port A, whatever is the port A available, that will be your digital thickness. So this is digital to analog converter interfacing, right? So timing point of view, so once you give this start of conversion signal, right, start of conversion signal, then you are checking for end of conversion signal, right, end of conversion signal here. So if it is low means you wait, if it is coming high means the data is available, that data you can, is it all right? Yeah. So this is what the sequence is in terms of timing diagram. Okay, start of conversion signal, end of conversion signal, A and B, then the data ready. So you can take this kind of problems to interface analog to digital converter to 8085 and write an assembly language program to read digital value from ADC. So this is what the program, equivalent programs are available. You can try to take up this. So is it all right? Yeah. So this is what a little bit difficult. This is what a little bit complex, and because this is very interesting subject. Where you have to know the hardware. Once knowing the hardware, and if you know the hardware, then algorithm and then program it should go upon. So you will try in your lab interfacing of, and most of the colleges I think they skip this lab, this particular experiment, because they feel this is very difficult. But now it becomes very easy for you. So now you can go ahead. Right. So the moment you know the sequence, and it's very important. It's very important if you are doing an Arduino programming, or if you're doing a microcontroller programming. Right. These steps, what we did here, instructions we are using 8086 instructions, but there it is 8051 instructions or Atmel instructions you will be using. But procedure is same. Because after all, by using all these programmable devices, we are processing real-time information, right? So we are processing the real-time information means these steps, on microcontroller on-chip AD converter is available. Here in microprocessor, we are interfacing one IC to 8086 and then we are reading the outside world data, right? So this is very important. That's why I took up to 1 hour to complete this particular topic, yes, right? So it's very simple now for you, I guess, and then you can go ahead. Then now next we will move on to the next topic. So with this all interfacing in our third chapter, I think we finished it. Now let me show you the syllabus of your let us review what exactly we are studying up to now, so that we can, yeah, so this is what your syllabus. And first chapter we finished. Second chapter, I think programming point of view, 1 or 2 classes I'll give you. Addressing modes and programming steps, development steps is what we have seen. But I think due to holidays and all, we couldn't cover this much. But 1-2 classes, if it is available, then we can finish. And now third chapter, if you try to see the third chapter, so we've interfaced this part we covered, interfacing memory to 8086 processor, and interfacing programmable peripheral interface is what we have seen. So this part is covered. Programmable peripheral interface is what we covered, right? And semiconductor memories interfacing is what we have seen already, and stepper motor interfacing is already we have seen, and analog to digital converter and digital to analog converter is also finished now, right? So this is an experiment point of view. I think most of the colleges you have these things, so you can practice in lab. So that so I covered this. So now what I try to take now, the next topic is programmable interface. Programmable timer and counter is what now I am going to deal, and rest. And here I think some more examples are there, like how to interface LCD to 8086 processor, but this in detail I'll try to take when I try to deal with microcontroller. So in microcontroller interfacing also we will see this particular point. So here in microcontroller you have 8051, and then again here you have analog to digital and digital to converter interfacing, and LCD interfacing is important. So there I'll discuss the detailed about LCD interfacing, right? How LCDs are interfaced to microcontroller. Same concept you can apply here. So even that part I'll try to take up there. So now few other peripheral very important. They are 8254, 59, and DMA controller 37. Right, 37. So these 3 ICs is what I'll discuss, so that the third chapter we can finish, and then we can go to microcontroller. Then after completion of microcontroller, we can come back to the advanced microprocessors. This is how I am planning the syllabus. Right. So now let us move to the next topic. So now let us move to the next topic, that is programmable peripheral and programmable interval timers. Right? Yeah. So why this is important? Programmable interval timer. Each programmable device which we are designing, including your computer, should have a real-time clock. See, the moment you open your computer, you try to see on the right side what is the time now and what is the date today, right? So that is a reference time your processor has to work on. So there should be a timing sequence for every programmable device. You need to interface 8254 or 53, 8253 or 54, which is timer. to our microprocessor here. So how to do this particular thing is what we try to see in this particular lecture. So that means the basic thing is giving timing sequences or giving references to your system, whatever the programmable system it is. Okay. So now let us go ahead. Now, if I want to give a delay, right, see, yeah, this is what an example. Move CX comma 400, loop wait there only. So this just now we have seen this. So it is called a software delay. So if I want to give a delay, sometime, that means, let us take in an industry where the bottles, it is a Coca-Cola company kind of thing you can consider, where bottles are filled with Coca-Cola and moving on a belt. So then you have to count them, right? So then the space between one bottle to another bottle, one bottle to another bottle, that means, the space is prefixed, if you know, then you have to wait for that particular time and then you have to read. So this kind of situation, you can take an example. It is just like the example I'm giving. So then sometimes we need to give delay to the system, so you have to stop for some time. So then generally we can give it through software, writing instructions. Move CX comma 4000 and then loop there only. But when this is done, what happens? Your processor is held up in executing. Your processor is held up in executing instructions. So it is not able to do anything else. Right? It is not able to do anything else. So time delay becomes an inaccurate if the processor is interrupted. So then the solution what we do is the timing with hardware which is programmed by the software for the specific delay. That means we use a submaster for giving delays and then giving counting sequences can be done by using a particular specific hardware. That hardware is nothing but this 8254 is. So at the end of the delay, the processor is interrupted. So the advantage is that processor is free for other kind of execution, multitasking it can go for. So while the hardware is performing the time delay. So the programmable hardware for specific delay is 8254 and 53 ICS. Okay. So now here we'll try to see the pin diagram, block diagram, and what are the different modes of operations of 8254, and how to, if I want to count a sequence, then how to write control word, and when the counter is counting, to know the status of a counter, then how to read from the counter, and what are the different modes of 8254 is what we'll try to see. So what is 8253 or 54? This is a programmable internal timer or counter, and it consists of 3 internal counters, each is of 16 bit. 3 internal counters, right? So they can be programmed to count 4-digit BCD. That means you can count from 9999 to 000 in decimal, or in binary count also you can go for FFFF to 000. So they are down counters. The 8254 has 3 counters. They are down counters. The counting can happen in BCD or hexadecimal. So they are 16-bit synchronous presettable down counters. The counters can be cascaded by connecting the output one to the gate of the other. So you have a 16-bit counter, 16-bit counter. So the output of one counter can be connected to the input of another counter by using a pin called gate. You will see that. So coming to the applications of 8253, you can use this in real-time clock, and you can use this to give specific delay, hardware delay, and you can use this for frequency synthesis. You can use it for frequency measurements. You can use this for frequency measurement, and you can generate pulse width modulation too. Right. So in your computer, this timer also appears in our personal computer, and the port addresses of the timer which is available in our computer is 40 to 43, 440, 41, 42, 43. The IBM PC, the personal computers, they have the timer, and then they are given the addresses 40, 41, 42, 43. So these will generate a basic timer interrupt that occurs at an approximately 18.2 hertz. A timer interrupts, the timer interrupts the processor every 18.2 hertz. And it is used to refresh DRAMs. DRAM, dynamic need to be refreshed, right, after each specific time. So for that sequence, I think you can use this and provide a timing source to the internal speaker and other devices. Right. So our basic processor would be is working with very high frequencies, megahertz, gigahertz. If you need low frequency signals, I think we can divide the counter. Okay, we can generate any pulse of any square wave of different frequencies by using this 8254. And now coming to the hardware details of 8254, it is a 24-pin IC, and now if you check it out, that block diagram, it has 3 counters. See this. So it has, nothing to confuse and all. Right. So here you have counter 0, counter 1, and counter 2. So these are what? 16-bit counters. So these are 16-bit counters, 3 counters. See, 8255, and if you see the block diagram, it may be looking same, but here you have ports there. Port A, port B, and port C, right? And everything, other things are same. So here, to interface this IC to microprocessor, they have internal data bus D0 to D7. So this is data bus buffer. And here you have read bar, write bar, A0, A1. So this A0, A1 is used to select counter 0 or counter 1 or counter 2. That we'll see in detail. And if you want to write the counter to be count a particular specific, so then you can use this read bar and write bar, and you can read the status of the counter when it is counting. What is the status? And this particular IC is selected by using chip select. When it is low, then this IC is selected. And A0 and A1 are to select either the control register, control word register, or counter 0 or counter 1 or counter 2. So mainly you have 4 things in important. One is the control word register, another one is counter 0, counter 1, and counter 2. So 4 addresses are needed. So each counter can be taken as an IO device, output device. So 4 addresses are given. That's what we have seen now: 40, 41, 42, 43. So 40 would be counter 0, 41 is counter 1, 42 is counter 2, and 43 is your command register. So 4 addresses. The addresses can be of 8-bit addresses, and the addresses can be of 16-bit addresses. So now if you check it out, 8 pins, anyhow they are the data bus. And here you have write bar, read bar, chip select, A0 and A1, VCC and ground. So the leftward pin are 3 counters you have. Each counter has input clock frequency, and it has a gate pin, and the output of the counter you can see on out. So clock, gate and out for each. So 9 signals for that. So this is of total 24 pin IC. And now, as I said, now when A0 and A1 are used to select counter 0 or counter 1 or counter 2 or control register, when A0 and A1 are 0 0, counter 0, and when A0 and A1 they are 0 1, then counter 1, 1 0, then counter 2, 1 1 and the control register. So a total of 4 ports are needed for single 8253 and 54 timer ICs. And now, when A0 and A1 they are 0 0, then counter 0 is selected. So if chip select is 0 and read bar is 1 and write bar is 0, means write into counter 0. So similarly, you can go for counter 1, counter 2, counter 3. You can write into the control counter to now start counting from a specific word. And when it is 1 and 1, then you write the control register 0 1 0 1. You have to know the hardware, otherwise. And reading operation can be done based on your read signal. It has to be 0, and then write signal has to be 1. And you can read a counter 0, a counter 1, counter 2 based on these things. So you can read or you can write. So inside of the counter, if you try to see, you have a clock input signal, you have gate signal and output signal. And this counter is of 16-bit counter. Then you have the count of LSB and MSB. And you can latch the count, and then you have the latch register. So here you have the count register, here you have the latch register. More in detail, if you want to see, this is what each counter is what you can try to take. Here you have the control logic. This is what your counter, counting element. It is counting. So then the status of the counting you can know by using status register. And once you know, you can read the content of this by using status latch. Or whatever the status of the counter, you can latch it. And OL is the output latch, so whatever is the counter it is counting, then you can latch it at any particular moment. So lower byte and higher byte, you can latch it. And CR is the counter register. So whatever the count you have to, your counter has to start with, we will write that into lower byte and higher byte. So first we will write the lower byte, then we will write the higher byte. And configuration of this is done by using control word register. So this is in particular one single register, one single counter is. So the clock input frequencies you can give between 0 to 2 megahertz for 8253 and 0 to 10 megahertz for 8254. This is the reference. 8253 means the clock you can give up to 2 megahertz only, but 8254 you can give up to 10 megahertz. And the out, after being divided, the shape of the output frequency from this pin can be programmed. Square wave or one shot and all you can get from this out. And gate enables or disables the counter. So for enabling a counter and disabling counter, you can use the gate. If high on the gate enables the counter and low on this disables the counter. Is it all right? So these are the details about the 8254. And coming to the interfacing, how you can connect this to the 8086 microprocessor means this is how you can connect. Now let us take 8253 and 54 are connected like this. Then here M by IO bar of 8086, read bar and A0. So it is IO read. IO read is connected to read bar of 8253 and 54. and right bar, this is decoding logic, simple decoding logic, and right bar is connected here. And A1 and A0 are used to select either counter 1 or counter 0 or counter 1 or counter 2 or the control register. So now here this pin has to be selected, means all these should be 0 0 0. This is OR gate. When they are 0 0 0, this is 0, then this pin is selected. So A15 to A3, they are all 0 0 0. And A1 and A2, if A1 and A2, they are connected to A0 to A1. So A0 to A0 and A1, they are 0 0 means what? Counter 0. So then counter 0, A1 and A2 0 0 means counter 0. 0 1 means counter 1. 0 2 is 1 0 is counter 1. Counter 2, and then this is counter 3. So the addresses for this is 0 0 0, the 16-bit address. So 0 0 0 is counter 0. 0 0 0 2 is what? Counter 1. Because the A0 is generally went for address decoding logic. So A0 we are not connecting here. So this is always 0. So it is 16-bit interfacing. And now 8-bit interfacing, this one. I0 by M bar, 8 bar and right bar. So now A0 and A1 are connected to A0 and A1 of the processor. So then if it is 0 0 counter 0, 0 1, 1 0 and 1 1. So if it is 8-bit, then 0 0 0 1 0 2 0 3 is what the addresses of your 8253 is. So take down an example. If CS bar is given 8253 is activated by binary address, then find the port addresses as assigned. Very simple. So you can take this 8-bit, A1 and A0 are responsible. So 94, 94, 95, 96, 97 are the addresses. This is what mapping, connecting external devices to your 8254. So I stop here. So we have seen just the details of 8253 and 54, and programming of this 825354 will be dealing in the next class. So as the time is up, then I'm stopping here, right? So we will meet. So what we discussed today, we have seen the interfacing of analog to digital converter thoroughly, and we wrote algorithm and we wrote program. And now how to interface one more important IC, that is 8254. That's hardware details is what we have seen now, and rest we'll try to take up in the next class. So is that all right? Yeah.